Good morning. All right, we're just gonna jump right into it. So remember, we've got we've got a test coming up next Tuesday. We won't have a review day, so but I will have a practice test for you guys. I haven't made it yet, but no classes tomorrow, so maybe I can make it then. So we've got test number 2 on Tuesday, November 17th. It's going to be on chapters 2 and 3, and however far we get through chapter 4 next day. And up to the end of next day, right? Which is on chapter 4, which is exponentials and logarithmic equations. So we'll see how far we get into there. I don't think that we'll be able to finish all of that chapter, so that's okay. Kind of less on this test, keep a little bit for the next test. Remember, I want to have a test right at the end of the term, probably worth a little bit less because it'll be right before the final, but that way you've been tested on all the material that you need to have under control for the final. So that's why I do that. Okie dokie. Let's see here. So just for some review, okay, we were graphing rational functions, and to be perfectly honest, I didn't do a great job with you guys. However, I feel like I did a smashing job in the next lecture. So if you're watching videos, then see the Math 120 video from November 5th instead of ours. Yeah, that's usually, I feel bad for you guys. I wish that you guys could trade off being first and second, because I do with you guys, and then I realize some things that I should change, and then I change it for the next one, and they get a more refined lecture. For some reason, it's taking me longer in that lecture than with you guys, so something, I don't know, it's weird. Not usually like that. Anyways, so so if you want a better run through, because there's a lot of confusing stuff, and I'll make the pieces fit together today, or try to. But if you want a better run through than we had last day, then if you're checking the videos, you can check out the Math 121 instead. They're the same. Okay, so, but we were graphing rational functions. Rational functions, right, are a polynomial over a polynomial. So rational functions. Okay. And we had established a framework, right? So some step-by-step things that we're going to do to graph this thing. And remember, we're just sketching, and then we're going to check our work using Desmos. So I just need you to be able to find things like, where are the asymptotes, where are the intercepts, right? And that kind of, what's the end behavior, right? And so the first thing you're going to do is to factor the numerator and denominator. The second thing you have to do, right, is to find the intercepts. Find the intercepts. remember the x-intercepts are where the numerator is 0, right? Where y is 0, but y, if you have y equals p of x over q of x, where each of these are polynomials, right? If y has to be 0, the only way I can force that is if the numerator is 0. So the x-intercept is where the numerator is equal to 0. Right. Technically where y is 0, but that's how we force y to be 0. The y-intercept is, of course, where x is 0, so you plug in x equals 0 into the equation. The y-intercept is where x equals 0. Okay. So that's how you find the x and y-intercepts. There are cases where there may not be an x or y-intercept, but usually if I'm getting you to do it, there will be some. The third step is to find the vertical asymptote. Plural, potentially. Okay. The vertical asymptotes are where the denominator is equal to 0, right? We can't divide by 0, and so wherever we would be dividing by 0, that's where we find these vertical asymptotes. Where the denominator is equal to 0. Right? So that's what's nice about having factored both the numerator and the denominator, is that, okay, well, figuring out where the numerator is equal to 0 is easy because we've already factored. And where the denominator is equal to 0 is also easy because we've already factored. Oh, I forgot a step for the vertical asymptotes. Are where the denominator is equal to 0, and then we use test values to see if it's going to go to positive infinity or negative infinity at that point, and we do it from the left and from the right. So, and then use test values to determine the behavior around the asymptote. Both from the left and from the right, right? We have to approach it from both sides because they could have different behaviors. Both from the left and right. Okay. Step 4, almost there, is the horizontal asymptote, right? So horizontal is straight across like this. So this is going to be the end behavior of this thing as it's going out. And we can have horizontal asymptotes at a different value of y, or at y equals 0, or there may be none. Right? So a horizontal asymptote The horizontal asymptotes, remember, depend on the degree of the numerator and the degree of the denominator. If n is the degree of the numerator and m is the degree of the denominator, denominator, right? The first one here, I'll actually use just little dashes here. If n is, and what did we say, less than m, there's an asymptote. Actually, I'll just use HA for horizontal asymptote. It'll be a little bit cleaner. I'll just establish that here. Horizontal asymptote, and then of course we use VA for vertical asymptotes. So if n is less than m, so the degree in the denominator is higher than in the numerator, and I'll make this look like a better thing. There's a horizontal asymptote at y equals 0. Okay, so on the x-axis we have this horizontal asymptote. And I'll remove that because it looks like a negative. If n is equal to m, there's a horizontal asymptote at an over bm. Remember what those are? These are the coefficients, the leading coefficients of the numerator and the denominator. Where an and bm are the leading coefficients of the numerator and denominator, respectively. Okay. And our last option, right, is if n is greater than m. If n is greater than m, then there is no horizontal asymptote, right? So that can happen. Okay. The final step is to actually draw these things. So what you're going to do is you're just going to sketch out where your intercepts, where your asymptotes. You've already established the general behavior of the vertical asymptotes. And then from the graph, you'll be able to see what the horizontal asymptote looks like. So your fifth step is sketch the graph, including all the components you found above, all the components you found above. Okay. That's the one that I'm interested in, but then check your work using Desmos. Sometimes there are little things that we might have missed, and I want to go through an example where it's a little bit different than what we did last day. And then, of course, check your work using Desmos. Okay. So I'll call this the end of the review, and then we'll start with an example here. Any questions though before we do? I'm keeping an eye on the chat, but it's pretty quiet out there today. And that's okay. All good. All right. So if I want you to graph r of x equals x squared minus 2x plus 1 divided by x squared plus 2x plus 1. So this one's a little bit special, and I just want to highlight so that we know how to deal with these ones too. The steps are all the same, it's just at the end in our sketch that we need to kind of work on some stuff. All right. So step 1, right, is to factor this thing. And you can absolutely use the quadratic formula, right? We've got a quadratic over a quadratic. And so you can factor this however you want, but step 1 is to factor. And so I'm going to write r of x is and x minus 1 times x minus 1. And you can confirm it, right? If you expand this, x squared minus x minus x minus, or -1 times -1 is +1. So I get x squared minus 2x plus 1. So I'll just confirm that up here, x squared minus 2x plus 1. You don't want to factor without checking that you've factored correctly unless you're really, really confident. I am not. I always end up checking my factoring. And then x squared plus 2x plus 1. So it has to add to 2 and multiply to 1. Sounds like x plus 1 times x plus 1 to me. Okay. If I expand this, I get x squared plus x, so that's 2x plus 1. Great. I'll use a different color here. Okay. So we've factored this thing, but notice how there's x1 squared over x, or x minus 1 squared over x plus 1 squared. So r of x is x minus 1 squared over x plus 1 squared. Okay. We say that this is a factor of multiplicity 2, okay, because it occurs twice, right? And so this is going to come back later in the behavior crossing the x-axis. Okay, so I'm going to bring that up, but it's just in case you see something like this, especially here in the denominator, right? Well, and then in the numerator, where you have these multiplicities. Factors of multiplicity 2. These behave I don't know, slightly differently than regular factors. These behave in a unique way when sketching. Okay, so just kind of stay tuned. I'll bring it up when we need it, when we're sketching. But until then, we can just go ahead and we can find the intercepts. So step 2, I'll put it on the next page here, is the intercepts. Okay, so the x-intercepts are where the numerator is 0, right? So where y is equal to 0. So it's the x values that make the numerator 0. In this case, it's going to be at 1, right? X equals 1. 1 minus 1 is 0. So it's where x minus 1, squared equals 0. And of course, we can kind of square root stuff and we can move things over. But what you would find is that it's at x equals 1. Okay. And it's the same for both of these factors, right? Because they're the same. 1 minus 1 is 0. And then again, 1 minus 1 is like 0 again. So it's 0 times 0, but that's still 0. Okay, so we have one x-intercept at x equals 1. Okay, that's fine. How about the y-intercept? Is where x equals 0. And what I like to do is, it's nice to put it into the original equation just so we can make sure that we're on the right track, right? So, or you can put it into the factored equation if you're feeling really good about your factoring, but I like to put it into the original equation, which I'm just going to steal and bring down here. So r of 0 is 0 squared minus 2 times 0 plus 1. Notice that the math is really easy here. 0 squared plus 2 times 0 plus 1. So r of 0 is 1 over 1. So the y-intercept is at y equals 1. Right? Or at 0, 1 if you prefer the coordinate point. Okay. Here, this is at 1, 0, right? X is 1 when y is 0. That's the x-intercept. In fact, I'm going to do these in the same color so we have the points in the same color, or 0, 1. Okay. All right. So we've got the x and the y-intercept. That's a good start. So now let's deal with our asymptotes. So the third step is the vertical asymptotes are where the denominator is 0. Okay. Our denominator is x plus 1 squared. So x plus 1 is going to be 0 when x is negative 1. So we can do x plus 1 squared equals 0 when x is negative 1, right? If you want to take the square root of both sides, square root of 0 is 0, x minus 1. Okay. Or you can just look at this, 0 squared is still 0. So x plus 1 means that you have a vertical asymptote, so straight up and down at x equals negative 1. Okay. So now we need to know the behavior as we approach negative 1 from the left and negative 1 from the right. So now find the behavior as x goes to negative 1 from the left and as x goes to negative 1 from the right. Remember this notation that we use, so a little superscript of 0. Why did I say 0? Negative is, so we've got like a dump truck convoy going back by here. Anyways, a superscript of negative means going from the left, positive from the right, right? So we're approaching negative 1 from the left and from the right. So I think the easiest way to do this is just to put a number line out, and then we pick test values, but we just need to know if it's positive or negative. Well, what's nice about this is we only have one vertical asymptote to check here at negative 1. And so here, x is approaching negative 1 from the left, and over here, x is approaching negative 1 from the right, right? Coming in to negative 1 from the right, coming into negative 1 from the left. It's possible that it goes down from the left and up from the right. We saw that last day. So now it's easiest to just kind of pick some test values close to negative 1, but not negative 1, right? And put it into our factored equation. So our factored equation is this one here, right? X minus 1 squared over x plus 1 squared. Rx is x minus 1 squared over x plus 1 squared. Okay, and just picking some test values here. To the left of negative 1, let's say it's negative 2, right? And then to the right of negative 1, I like 0, right? Whenever I can, I'll use 0. And so what we have here is we have, let's pretend we put in negative 2. Negative 2 minus 1 puts me at negative 3. But then when I square it, I get a positive value, right? So this becomes a positive value. In fact, whenever I square anything, I'm going to get a positive value. And so it's a positive over a positive, which makes a positive overall. What that tells me about the behavior here, as I'm approaching -1 from the left, it tells me that I'm shooting up to positive infinity, right? So what this thing looks like is we might have something like this, right? Doing the same thing to see if we get a positive or negative value as we approach -1 from the right. Okay, so again, now I'm going to plug in 0. 0 minus 1 squared, -1 squared is still positive. Again, any squared value is always going to be positive. And so I get a positive over a positive, which is a positive overall, which means here I might have something that looks like this. Okay. All we know is that as we get closer and closer to -1, right, we start shooting up and we go towards positive infinity. Okay. I'll put positive infinity here just to emphasize that that's what we established here with these positives. Okay. I'd say the vertical asymptotes, dealing with the vertical asymptotes is probably the hardest part after you factored, of course. If you're like me, I don't like factoring. I don't think it's easy. I don't see it. You just need to work at it, right? And you can always use the quadratic formula. And then sometimes you kind of get sick of using the quadratic formula and you're like, hey, I see it. So that's where you want to get to, right? You've done enough of them that you kind of start to be able to factor more easily. Okay. So the horizontal asymptote is quite a bit easier, right? So the horizontal is the fourth step. The horizontal asymptote is, well, in our case, the degree of the numerator is 2 and the degree of the denominator is 2. Notice that the coefficients, they each have a coefficient of 1. Okay, so what I'll do is I'll just copy this again, bring it down. Oops. N equals 2 and M equals 2. And AN over BM is 1 over 1, which is just 1. Okay. So because N is equal to M, which is equal to 2, okay, so what we can say is, since N is equal to M, which is equal to 2, indicating that they're the same, right? We have a horizontal asymptote at y equals 1 over 1, which is 1. So at y equals 1, we have this horizontal asymptote. The horizontal asymptote, right, it's just the end behavior, right? So as x goes to positive and negative infinity, then y is going to approach 1, right? So it's going to either settle on 1 or go up to 1 and kind of plateau off. It's never going to reach 1. And that's kind of hard to know in your sketch what it looks like. So let's have a look here. Here's our sketch. You know what? Sure. Put a little grid on here. It's hard because they never, I can never move them. So once I'm committed to this grid, then there's no changing it. All right. So let's outline some of the things that we need to put on here. Let's start with our intercepts. Okay, we had an intercept at 1, 0 and the y-intercept at 0, 1. Okay, so far I'm hanging out around the origin. I have a vertical asymptote at x equals -1. I know the behavior around there, and I have a horizontal asymptote at y equals 1. So it looks like I'm hanging out kind of around the ones. So no big deal. There's no like 10 that I need to incorporate or anything like that. So I'll just put it in the middle here. Okay. And I'll use 1 square per unit. Okay. So first thing I'm going to put on here is, well, my x and my y intercepts. I had them. 1, 0 and 0, 1. 1, 0 and 0, 1. Okay, so those are my intercepts. Moving on to the next step. Okay, so I've got my intercepts. I had a vertical asymptote at -1. So I'm just going to put kind of a, so at x equals -1, it's supposed to straighten out. Anyways, I have a vertical asymptote, and I also have a horizontal asymptote at y equals 1. So what I'm going to do, I'm going to put these on here. Okay. So these asymptotes, I'm never going to be able to be on them. What's tricky is I'm allowed to cross asymptotes as long as it's not in the end behavior. Okay. Because otherwise it makes it really hard to figure out what to do around here. It looks like, okay, well, I'm not allowed to cross here, but somehow I'm supposed to get to here, right? And so let's start with the vertical asymptote. So I already know from what I established here when I use my test values that around x equals -1, both of these are going to go up. Okay, so I'm going to put that on here kind of like this. And I'm not committing to anything kind of deeper down quite yet because I want to know, hey, what does this thing look like? Okay, so it looks like, let's start on this side, right? I know I can approach the horizontal asymptote, but I can't quite get to it. So in order to have this kind of increasing relationship, the most logical thing, and sometimes, I mean, we're not going to be sketching whizzes or anything, but sometimes you might be caught off guard and you might have missed an x-intercept or something. But for the most part, if we have this kind of upward behavior, the only logical thing is for this thing to be kind of sitting down on the horizontal asymptote. Okay, so I'm going to draw that in like that. Okay. Same idea on this side, right? If I didn't have an x-intercept, then it sounds kind of reasonable that it would just kind of jump down here and then just kind of maybe plateau off or maybe go just under and reach the horizontal asymptote. What happens is here, right, our x-intercept, remember we said it was actually multiplicity 2, okay? And so what's going to happen, and it caught me off guard too, so I'll admit to that. It's like, hey, why didn't it just go down? Okay. So what I initially wanted was, I said, okay, in my mind, I said, okay, well, I need to cross the y-axis here and the x-axis here, but then I eventually need to come up here. See, the problem though is if I'm going down underneath the x-axis, I would need to come back up in order to reach this horizontal asymptote. We already established that there's only one x-intercept, so that's not happening. So what happens is we need to remember that this x-intercept was actually multiplicity 2. Okay? And that's why it's going to go down here. okay, cross the y-axis, or yeah, cross the y-axis at 0, 1, and then it's gonna just bounce off of 1, 0, and then gonna go back to the horizontal asymptote from below. So here, now, you can go like this, and then it's gonna approach like that. Okay. Never crosses the x-axis since it is multiplicity 2. Okay, so I'm going to grab a quick note that I think we kind of skimmed over in 3.2 because we didn't quite need it, but I'm going to bring it in here if I can. Okay, so here, if C is a 0, so a 0 is an x-intercept, okay, of multiplicity m, okay, so in our case we have multiplicity 2, then the shape of the graph near C is as follows. If m is odd, which it isn't in this case, if m is odd, then it's going to cross that at that x-intercept. If m is even, which it is in our case, then it just kind of bounces off, right? And depending on which direction you're coming from. So this is from 3.2. Okay. But that's what's going on here. Okay. But I encourage you to try as many of those sketches. So I gave you some, hey, where did they go? Functions. I'm going to bring it over to ours. So at the bottom of this page, right, in 3.6, you've got all these equations, okay, or all these rational functions. And I want you to try as many of these as you can. It's kind of nice because you can actually check your work using Desmos, right? And so you can always graph these in Desmos and make sure that you're on the right track. The one that we just did was this one, right? So we did 59 just now. So let's use Desmos to check these out. So we had x squared, oh, and I've got a polynomial as a fraction, so I'm going to put brackets around that just to make sure that I'm able to divide all of this. So x squared minus 2x plus 1 bracket divided by x squared plus 2x plus 1. Okay. Here I had to zoom out all weird. For that other question that I was working on. How can I change my axes here? Let's see here. My y-axis is going to go from -10 to 10, increase by 1, -10 to 10 by 1. Okay, so now right? It looks like what I had before. Okay. What you can do is you can put on your asymptotes. So at x equals -1, it looks like that is the asymptote that they're following, right? So that's good. If we do one at y equals 1, it also looks like that's the horizontal asymptote that we're following. And it confirms that we cross the y-axis at 0, 1, and we bounce off the x-axis at 1, 0. Right? So anyways, that one's a little bit strange just because of this behavior down here around the x-axis. But it's because of that multiplicity in the factors. And okay, so the last thing I want to talk about from this section is the common factors in the numerator and the denominator. Hey, I thought I named this. Yeah, I did. Okay. So far, okay, we've been saying that the numerator and the denominator have no factors in common. That's not always the case, right? If that is the case, so if they do have a factor in common, then we can cancel that factor, that's fine. But what we have to remember is that, okay, well, we've canceled something, which means it was in the numerator and in the denominator. I have to remember that I can't divide by 0. Even if I'm able to cancel it away, it was still there to begin with, right? And so, so what happens is we get a hole in that space, right? So here I picked an example, just a quick little example for us to go through. So for example, if we have s of x is equal to x minus 3 over x squared minus 3x, there's nothing to factor up here, right? X minus 3, there's nowhere to go. But I can pull out a common x here, right? And so what I get is this becomes x minus 3 over x times x minus 3. Hey, what'll you know? What do you know? Looks like I have a common factor of x minus 3. Common factor of x minus 3. The way this is laid out, I am able to cancel this, but because this is the equation that I'm dealing with originally, right? Originally, there was an x minus 3 down here. So even when I cancel it, I have to remember that x can't be equal to 3, right? So down here, right, x can't equal to 3. And of course, x can't be equal to 0 because I can't divide by 0. 0 times 0 minus 3, 0 times -3 is 0. Dividing by 0, no go, right? So x can't be 0, but also x can't be equal to -3, or sorry, 3, because 3 minus 3 is 0 times 3, 0 times 3 is still 0. So you're divided by 0. So even when you cancel, you have to pull out this x equal to 3, right? So x can't be 3 because then you would be divided by 0 in the original equation. So now what we say is we have a hole at x equals 3. So even after we cancel, the common factors, or the common factor of x minus 3, we need to remember that x equals 3 is not in the domain of the original function. We need to remember that x equals 3 is not in the domain of the original function. Okay. So this will kind of end up looking like a hole at x equals 3. We have a hole at x equals 3. Okay. So what we end up doing is we have s of x is x minus 3 over x times x minus 3. Okay. This is going to cancel, this is going to cancel. And so s of x is just going to simplify to 1 over x. Of course, 1 over x, we can see that x can't be 0, but we also need to add that x cannot be equal to 3. Okay. And so what we'll do is we'll graph this in Desmos just to make sure that that's what it looks like. So we're going to graph, of course, this original x minus 3 bracket x minus 3 and bracket divided by x squared, shoot, where was it? Minus 3x. Okay. Hey. Come on. See, it's not obvious. I have to kind of be super close, I guess. Maybe. But once you hit 3, it confirms that it's undefined. I'm trying to hold it as steady as I can there, but it's really hard. Trying. Hopefully you've caught a glimpse. So at 3, it's undefined. There. Oh. Okay. And then it just keeps going. So then the rest of the graph looks like 1 over x, but we're going to have that hole at x equals 3. So we have something that looks like this. This is 1 over x. And then at x equals 3, we have this hole. I'm going to do a partial eraser here, like that. Okay. Good. All right. So I'd say that's the end of chapter 3, which is a lot of graphing, right? We graphed quadratics, we graphed rational functions. There's a lot of stuff going on, right? So you'll want to make sure that you have your notes organized so that you can graph a quadratic, so that you can put together some graphs like this. Right? The test. Okay. So, chapter 4, if there are no qualms, is on exponential and logarithmic equations. Okay. Exponents and logs. Oh, I guess I should. Logarithmic. There's an I in there too. Not obvious. There. So exponents and logs are usually, oh yeah, so chapter 4 is, do you mean chapter 4, Kayla? Yeah. So chapter 4 up until the end of next day will be on the test. Okay, so because we're just kind of establishing exponents and logs, everything up until the end of next day will be on the test. Okay. Good. I think what you'll find is that exponents and logs are a lot nicer than graphing nasty rational functions, for example. And so hopefully you'll kind of enjoy this section a little bit more. I know I do. Usually what happens is you guys like stuff that I don't like, and I like stuff that you don't like. But exponents and logs are really important, especially if you're dealing with things like concentrations, which I know you guys are doing a lot of, and things like that. So you will be dealing a lot with exponents and logs. There's only so much that we can do here, but I'll introduce them and teach you the laws of how to use them and calculate things with them. And then you'll have it for the rest of your courses. Okay. So let's see here. I haven't grabbed it, I don't think. Gotta log in, of course. It always wants me to log in. So I posted some assignments, right, from 3.2, 3.3, and 3.6, as well as the solutions. So 3.1 was in week 8. I have the solutions already for feeling so on top of things for chapter 4 as well. So if you're working through the problems in the notes, right, then you've got the solutions already. So I know it's the little things. Mm-hmm. Okay. Here we go. So exponential functions, you've probably heard statements like, oh, it increases exponentially, right? Exponential growth, exponential, right? And so what that means is that things start kind of slowly to grow slowly, and then they kind of take off, right? So, and what that looks like is like this, a to the power of x. So I'm going to steal this in here. So an exponential function, oh, I guess this is section 4.1. 4.1 is called exponential functions, just in general, introducing them. So an exponential function with base a, so we need to establish, okay, some terminology around these things, just like when we were talking about fractions, and we have to know that the numerator is on top and the denominator is on the bottom. Otherwise, it's really hard to talk about fractions. So now we need to establish that, okay, whatever is in the bottom here is called the base. Okay? And we can have something like f of x is equal to a to the power of x. So what makes it an exponential function is that the x is in the power. Yeah. When x is in the power, we have an exponential function. Okay. We're establishing that, okay, a is going to be greater than 0, so we're not going to deal with negative a quite yet. And a is not equal to 1. 1 to the power of 4 is just 1 times 1 times 1 times 1, right? And so, but we know that 1 times 1 times 1 times 1 is just 1, so it's not very interesting. So that's why we have a not equal to 1. Okay? So a to the power of x is going to be a times a times a times a times a x times. Okay. So a to the power of 4, for example, is a times a times a times a. Right? It's just a cleaner way of writing this, and we've already used that, right? We just saw it in x minus 1 times x minus 1. We kind of zipped it up as x minus 1 squared, right? Same thing. So now, because this x is in the power, so now we're able to vary how many multiples of a we have, right? This is what makes it an exponential function, right? When x is in the power. So let's bring in this next one here. So the graphs of these things, okay, either go and kind of start slow and then they increase rapidly after some point of x, right? So they just start kind of increasing, or there's this decay. So here we call this growth, so exponential growth and exponential decay. So this we call exponential growth. And this we call exponential decay. Right. And the difference between these are in the base, right? So if you have a to the power of x, as long as a is greater than 1, then you have this growth. Whereas if a is between 0 and 1, right, so it's still positive, but it's a fraction between 0 and 1, then you have this decay, right? And so if the base is between 0 and 1. Okay. Whereas the growth is if the base is greater than 1. Okay. Some other important things to talk about are the domain and the range, because we'll have to talk about the domain to figure out, okay, what am I allowed to put in here? What am I not allowed to put in here? Luckily, we have a domain of all real numbers. So the domain of this thing, the domain is that x is in the set of real numbers, or if you prefer, from negative infinity to positive infinity, right? So we're allowed to put in any value of x. That's nice. There are no restrictions on what we can plug into a to the power of x. We can plug in any power that we want, okay? What's important though is that the range, right? Notice that the range, we're always above the x-axis. Right, so the range is not including 0, so we'll never get to 0, but it goes up to infinity. Okay, so the range is going to be from 0 to infinity for both of these. Okay. So of course, both of these have the same domain and range, so that's nice. right? I can ask you, what's the domain? What's the range? You can look at them and you can say, okay, well, it looks like I know an exponential function is never going to get to 0. Because we've established that the base is greater than 0, right? That's the why we don't get to 0. Okay. So what these things look like, let's just grab this little kind of tree looking thing. So remember, you have exponential decay if the base is between 0 and 1. So different bases. So the yellow one here has a base of 1 over 10, right? Versus 1 over 5, 1 over 3, 1/2. So notice as your base gets larger, we kind of start bending out a bit and getting these kind of, so the yellow one is 1 over, has a base of 1 over 10. So it's closest to the y-axis, but also closest to the x-axis. So it's kind of more sharp, okay? Whereas the red one has a base of 1/2, so it's still decay, and it's the furthest away from the y-axis and also the furthest away from the x-axis, so it's kind of this more shallow decay. Looking at a large base, right? So a large whole number base, 10 to the power of x, for example, is nice and sharp, right? So the larger the whole value base is, the sharper it is, right? Whereas if you have y to the is 2 to the power of x, then we get this shallow kind of exponential growth, right? So here we've got whole values for the base, means we have growth. If we have a fraction for the base, it means we have decay. And so those are good to keep in mind. Let's just do one quick kind of calculator one, just so we can make sure that we know. Oh, the domain goes negative here. I'll go back there. So the domain is all real numbers. Okay. But the range is from 0 to infinity, not including 0. And I think that's probably what you mean. It's because we are not letting the base be 0. So if you have 0 to the power of 4, that's just 0 times 0 times 0 times 0, putting you at 0. But because we're forcing the base to be greater than 0, you can never get down below the x-axis. Cool. I know I should have put spaces here. Awesome. Good. Yeah, so what I want to do is, if you have a calculator that looks like this, or I don't know if I have my other one here, but kind of something like this, right? Let's just make sure that we know how to use our calculator, because what a silly thing to have happen later. Okay, so let's just make sure we know how to do, you know what? No, let's do a harder one. We're just using our calculator. Let's do 10. Okay. 4 over 3 is my base, right? And my power is 3x. Okay. So what I have, I want to find, so g of x is 4 over 3 to the power of 3x. So now wherever I see an x, I want to replace it with negative 1/2, right? And then root 6, and then negative 3, and then g of 4 over 3, just so I can work on my calculator and make sure that you get the same values that I do. So g of x is 4 over 3 to the power of 3x. G of negative 1/2, okay, wherever you see an x, you're going to replace it with negative 1/2. So you get 4 over 3 times 3 to the 3 times negative 1/2, not 1/3. Okay. So just use your calculator, okay? So 4 divided by 3, whatever your calculator is, I like to do 4 to the power 4 divided by 3 first, and then I use my power button. And on mine, let's see if I can show you here. I've got this x to the empty, so then I can go that. And now in my power there, I'm going to put 3 times -1/2, and I'm using brackets. Okay. So I get this is approximately equal to 0.6495190.528. Okay. Make sure you get the same values. Right, just to make sure that you've got your calculator under control. What if we're doing g of root 6? So wherever you see an x, you're going to replace it with root 6. So you have 4/3 times 3 root 6. Oops, root x, root 6. Sometimes what's nice is you can simplify the power first before you plug it in. But what I'm going to do is I'm going to do bracket. And in fact, here, I guess I can use this Desmos calculator so you can see it instead. Maybe you're using this one. I don't know. I find it a little bit clunky, but it's okay. So I've got 4 divided by 3. Notice that I'm using brackets, and notice how the bracket here went a little mucky, so I want to step it out and close the bracket there. And then I've got the a to the power of b button here to the power of -3 times the square root of 6. Step out the, oops, there. Hey. Oh, it's a different one. Okay, I'm just going to make sure here that I get the same thing, just like you're doing. -3 times the root of 6. Oops. I get the same answer. I wonder if I can copy this. Oh, guess I'm writing it out. So you should have roughly 0.12075122231. Why -3? I used negative. I sure did. That's wrong. Why did I do that? No, 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 no. Yeah. There. I did it twice too, to make matters worse. 8.28. Oh, just keeping you on your toes. No, not really. Thanks for catching that. Should be 8.281489611. Hopefully that's what you guys got. Now I get to do -3. G of -3 is 4/3 times 3 times -3. I'll do it on here. Clear all. Bracket 4 divided by 3, step out, end bracket, to the power of 3 times -3. Oh, that's wrong. I want 3 times -3 in the power, which I mean, you could do 3 times -3 end bracket. Or you could just do -9 right away. if you're feeling confident. 0.07, so 4 divided by 3 to the power of 9. So this becomes 0.07508468628. Hopefully I copied that out right. 0.07508. Looks good. And I've got the end of my page here, so I'm not going to do the last one, but I'll tell you what it is. Maybe I'll squeeze it in here. 4/3 to the power of 3 times 4/3. Right, because x is 4/3. These 3's are actually going to cancel. And so I get 4/3 to the power of 4 which is roughly equal to 3.16049387. You don't have to cancel those 3's right away if you don't want to. You can just keep them in there, but it should be the same. No, I'm not going to focus on Sig Figs. I actually would prefer to see as many decimals as you can muster. Usually I like the exact answer, right, which would be 4/3 to the power of 4. But if you tell me what your how many Sig Figs you're using, then that's fine. But for math, we just want as many decimals as you can possibly get, right? Especially when you're doing approximations like this. So, yeah, we're not going to be focusing too much on Sig Figs. That's important for chemistry. You don't want to be more precise than your measurements, or pretend to be more precise than your measurements. Okay. Yeah, pi is 3. Exactly. We don't like that. It depends on what your field is. I know I talked to Allison about it, and she was kind of, Sig Figs, yeah, they're important. But we're talking about orders of magnitude, right? So depends on what you're talking about. But for straight math, we just want as precise as we can get. Usually we use exact values. All right. So I want to do one of these quickly, mostly because something similar came up on your assignment. We didn't really get a chance to talk about it. I think it was your assignment from, I want to say 3.1. Can't quite remember, but where you're given a point, right? And you're asked to figure out, okay, so I think on the assignment, you're given the vertex and a point that this quadratic goes through. And then you have to figure out what the equation of that quadratic is. So very similar to that, if you have a point, that means you have an x and a y value on this equation, right? So in this case, if you have f of x, which is actually your y, is equal to a to the power of x, if we know a point that this thing goes through, we're able to figure out what the x and the y are, and then we're able to solve for a. So 21. F of x is actually y, right? So if you think of it as y, then y is a to the power of x. Okay. And we're given given 2, 9 is on this graph. Right, so it's on this function. So what you can do is you can use x equals 2. When x equals 2, y equals 9. Okay. So what we'll do is y equals a to the x. We can replace y with 9 and a to the power of 2. And then we just need to find what a is to make that happen, right? So in this case, if we take the square root of both sides, okay, remembering that a has to be greater than 0. If we take the square root of 9, we actually get plus minus the square root of 9 is a. And so a can be plus 3 or minus 3. But a is the base, which must be greater than 0. Oops. So a is 3. Okay. So here, this equation must be a to the power of x, which is 3 to the power of x. Therefore, f of x is 3 to the power of x. Okay. So we can graph this in Desmos just to check, right? If I graph 3 to the power of x, keep doing y, there. Okay. Then at x equals 2, right? So what I can do is I can put a new graph on here, and I can either draw a line at x equals 2 or at y equals 9, because that's the point that I know. So let's do x equals 2 here, and it crosses at 2, 9, which is exactly what we wanted, right? And so we force that to happen. So you can check using Desmos, right, that we did this correctly, but it looks like we did, right? And so what you're using is this point actually gives you the value of x and the corresponding value of y. And then you're able to solve for one of the unknowns, a in this case. Okay. So I know you guys are, obviously I know you're in the wet program, which is awesome. But exponential functions are really common in interest, so money type of interest. Also things like population growth, kind of decay of elements, right? So radioactive decay, things like that. So exponential stuff happens in a lot of different areas. And so compound interest is one of those areas. And because it's got this nice real world application, I'm sure you all have some amount of money and you're going to the bank, or at some point you want to go to the bank and oh, the Weir model. I should write that down so I can incorporate it, because that's really good. Thanks, Tim. I've never heard of it. Obviously, I don't do any wet stuff, just math, but that's good. So a Weir model for water discharge. I'll have to look it up. That's awesome. Okay, but like I said, I'm confident that you have to kind of have some sort of understanding of interest and how interest at the bank works. And so I do want to talk about this one, but also because it's it's kind of a nice application of what we're studying. So in general, compound interest, and of course, if you want more on kind of money problems, there's business math, Math 114. Might be a nice break from your wet stuff. I don't know if you have time. But compound interest is when, okay, so you have $100 and you take it to the bank and they say, okay, we'll offer you 3% compound interest compounded monthly. So what that means is that at the end of each month, the bank goes in and says, okay, you've earned 3% on your $100. And then that 3% gets added to your $100. And then the next month you're adding interest, so 3% interest on the $100 as well as the interest from before. So that's the compound aspect of it. So you're compounding your interest after each compounding period. For us, of course, I would just give you the equation, but we have to know the A of t. A of t is the amount of money after t years. Usually we call this the future value, but we can call it A of t, it doesn't matter. P is the principal, so this is your initial investment. Initial investment. Okay. The interest rate per year has to be as a decimal, so it can't be, usually we talk about interest as percentage, but as a decimal, which means something like 7% is 0.07. Okay, you divide by 100. N is the number of times interest is compounded per year. So in our example, right, if the bank is compounding monthly, then we're compounding 12 times per year. And then the T is the number of years. So how many years is this thing, is your initial investment sitting there for? Okay, so let's do just a quick example. These are all the same. Let's just do one of these. Okay. We'll just do A. Okay. So, and I guess I'll kind of make it bigger. So if we have $10,000 invested, so that's our principal amount that we're depositing, and you can think of it as kind of a starting point for a population. They all kind of behave in a similar way. What's nice is I'll always give you the formula, right? So even though we've got this exponential function here, because the t, which is the variable, right, we're able to vary t. T is in the exponent, and so we have this exponential function. But I'll always give you whatever function you need, and then you have to plug things in and solve for whatever I'm asking for. So we have A of t is p times 1 plus r over n to the power of n t. Okay, so the t, this is our variable. Okay, so whatever is inside the brackets, that's your variable. So that's the thing that you're able to change, and essentially it's going to be your x. Okay, so your variable is in the power. So we have an exponential function. Okay. So if I want to know, okay, so my P is 10,000, so the P is the initial investment. So if $10,000 is invested at an interest rate of 3% per year, okay, compounded semi-annually, so twice per year, find the value of the investment after the given number of years. Now, I'm not expecting you, this isn't a business math course, so I'm not expecting you to know these semi-annually, biweekly, all those frequencies. I would just give it to you. But here, what we're saying is that P is 10,000 at a rate of 3% per year, so 0.3 or 0.03, 3% per year. Compounded semi-annually, so N is 2, semi-annually is twice per year. Okay. And for A, T is equal to 5. Okay. So we're going to solve for A of 5. A of 5 is 10,000 times 1 plus 0.03 divided by 2 to the power of 2 times 5. Okay. Just plugging in all these values into this equation here. Okay. And then I'm able to solve for the amount that I'll have after 5 years. You have to be careful because you want to solve 1 plus 0.03 divided by 2. So BEDMAS, right, brackets, and dealing inside the brackets, 0.03 divided by 2. Here we go. 0.03 divided by 2 is 0.015. So what I get here is kind of step by step, 1 plus 0.015 to the power of 2 times 5. I'm going to simplify to the power of 10. I still have to deal with the brackets, exponents, division, there's none, multiplication, yes, right? So I first have to deal with these brackets. So what I'm going to do is each of these steps, because we haven't done a ton of this kind of just algebra, right? We did before in chapter 1, but now we've been graphing mostly. 1.015 to the power of 10, so plus 1 to the power of 10. I get 10,000 times 1.160540825. So now multiply that by 10,000. I get 11,605.40825. If you remember, that's great that we can only have 2 decimal places for money, right? So money goes to 2 decimal places. I'd rather see all the decimals than too few, right? So what we get here is at 5 years, or after 5 years, I would have 11,605 and 41 cents. So you can use exponential models, and this is kind of a really typical exponential model, right? And it happens in the real world, so that's nice. We can solve for any value in here. Some of them are going to be harder and we'll have to leave for later, especially if we're solving for the exponent here. But we can solve for P if we have A of T, you want R and N and T. Right? We have to have all of the components except for 1 to be able to solve for it. So, good. I want to talk about section 4.2 is just a special case of what we just talked about. So exponential functions, it's on the natural exponential function. And the natural exponential function is just base E, which I'm sure if you've talked about these models before, then you've probably seen E the number, it's a constant. Let's see here, 4.2, the natural exponential function. So the natural exponential function is the special case where you have the constant E as your base. E is, oh, you know what, I'm going to move it over here. E is a constant, just like pi, right? And you get E, there should be a fancy E on your calculator, right? Mine is just red above the times 10 to the power of x, right? And it's beside the pi. You can't see that. Let's see if I can find it in here. Oh yeah, clear all. E in this Desmos calculator, if that's the one that you're using, where was it? It was in functions. Okay, so you have e to the x, and if I want to do e, just e on its own, that's e to the power of 1, right? And so if I go back here, e to the power of 1, the 2.718281828 is just an approximation, right? It keeps going and it never ends, just like pi. So we use 2.718 as an approximation, right? But you should be using your E button on your calculator. So E is roughly 2.7182828. I can't remember. There's a song. 2.71828. 2.71828. 1828. Roughly. Okay. So just like pi, 3.14, 2.72, I guess. It hurts. 2.718 is what I want to say. Okay. But E is just a special base. And usually what happens is that if we're talking about the exponential function, we have the specific base E. So behaves the same way. It's just E times E times E times E x times, right? But it's just a special case of the exponential function. Okay. So there's a definition of what E is. We're not going to talk about it. I'll leave it for if you go into calculus, then sure, we can touch on it, but it's not a big player. So just knowing how to find E on your calculator is great. So here, okay, what happens is, okay, so this red one is y equals e to the power of x. Well, if e is roughly 2.718, then knowing that it gets steeper as the base increases, right, we expect to see 3 to the x kind of closest to the y-axis. 2.7 is pretty close to 3, right? So we expect it to be somewhere between 2 to the x and 3 to the x, right? And so it kind of hangs out here closer to 3 to the power of x, but somewhere between 2 to the x and 3 to the x. Okay. All right. So maybe we shouldn't do this one. Maybe we'll do, because the answer is obviously in here. So you have that one in your notes. My bad. Let's see here. I want to do 27, but let's do 23 first. Okay. So notice that each of these, you're given the equation, so that's what you can expect, right? When a certain medical drug is administered to a patient, the number of milligrams remaining in the patient's bloodstream after T hours is multiplied, or is modeled by D of T, so the amount remaining presumably, is 50 times e to the negative 0.2 times t. How many milligrams of the drug remain in the patient's bloodstream after 3 hours? And so t is in hours, so that's the first thing we want to check, is check our units. I'm not going to try to get you with those, but it is good to kind of check them. So if t is equal to 3, then I'm able to substitute t equals 3 in here and solve for d of t. So d of t, just writing it out, is 50 times e to the negative 0.2 times t. So d of 3 is 50 times e to the negative 0.2 times 3. So we're going to solve this. E, I've already got e on here. Okay. So in brackets, just so I can keep everything on e to the power of negative, shoot, where'd it go? Negative 0.2 times 3, end bracket. Okay. And I can keep that there. So in Desmos, it's nice because I can kind of maneuver around my calculation here, and then times 50. So my answer is 27.4405818. So d of 3 is roughly, and I'll just do it on here just to be sure, 50 times e to the power of negative 0.2 times 3. And also, because it's hard to remember, roughly 27.4405818. Okay. It's an approximation because we'll never be able to get an exact answer if we're approximating e. So that's why we use the squiggly equals. How many milligrams? Well, the number of milligrams remaining is d of t, and so roughly 27.44. But I would just keep it like this, right? Technically, if it's asking for the number of milligrams, there are more than 27 but less than 28. It's easier, or it's safer in this case, since we're talking about how much is remaining in the bloodstream. It's safer to say 28, even though it's closer to 27. But that's the type of kind of nitpicky stuff that I don't expect you to do, right? As long as you're able to solve these equations, that's what we're doing. Okay. I want to talk about logistic growth. So for a lot of populations, what happens is, if we're talking about kind of a population in a limited area, and technically all area is limited to some degree, right? But especially if we've got this constrained space, then a population can only grow so big. right? And so animal populations are not capable of unrestricted growth because of limited habitat and food supplies, right? So there are some factors that that kind of come into play and limit our population size. So under such conditions of population, we have this logistic growth model, right? Where we start with some d over top and then over 1 plus, and then we have this exponential function in the bottom. So, and then we have to establish where C, D, and K, so C, D, and K are just constants, and they're going to be positive constants. For a certain fish population in a small pond, right? So now I'm giving you that D is 12,000, K is 11, and C is 0.2. So what we have to do is we just have to plug those values in here, okay? And T is measured in years. The fish were introduced into the pond at time t equals 0. How many fish were originally put into the pond? So remembering that P of t is the population size, right? And how many fish were originally put into the pond? Well, the fish were introduced into the pond at time t equals 0. So really what we're finding is P of 0. Make a couple of notes here. P of t is the population size at time t. So A, if P of t is, and I'm just going to plug in these constants so that I have it ready to go for this scenario. D is 1,200 divided by 1 plus K, which is 11, times e to the negative C, which is 0.2. And I'll just keep it general for now so that I can reuse it for the next problems because I'll probably need it. P of 0 is 1,200 over 1 plus 11 times e to the negative 0.2 times 0. Okay. So if you do e to the power of 0, right, negative 0.2 to the power of, or times 0 is 0. So e to the power of 0 is just 1. That's going to be a really good thing to have in your roster, right? So here, note e to the power of 0 is 1. Okay. So as soon as you see e to the power of 0, you can just replace it with 1. And so what you get is you get 1,200 divided by 1 plus 11 times 1, which is 1,200 divided by 12, should be 100. I just want to double check. Okay. And so initially, 100 fish were introduced, right? And that was the problem here. How many fish were originally put in the pond, right? Therefore, 100 fish were originally put in the pond. We can find the population after 10, 20, and 30 years. Let's find the population after 10 years, and then I'll leave the other two. And we can actually check them using Desmos. Okay, so I'll show you how to do that. And then we're going to see what happens for large values of t, right? So as t increases, what happens here? So B, P of 10 years, again, I'm just going to use that equation that I developed, 12,000 divided by 1 plus 11 e to the negative 0.2 times 10. So now I guess I can use the Desmos one. It's not as clean, but that's okay. What did we have? We had 1200 divided by everything in the denominator. 1 plus 11 times e, which is in the functions, e to the power of, and I'll put it all in brackets just to make sure I have it all, negative 0.2 times 10 and bracket. I'm at roughly 482.1817. Okay. Because this is a population, right, I have to round to a whole number. Usually what happens is we usually round up. If you went to 482, that's totally fine, right? But there's just a little bit more than 482, right? So what we'll say is after 10 years, there are roughly 482 fish. Okay. So what we want to do is, I'm just going to look at this in Desmos and try to answer these next few, right? And so let's look at this in Desmos, the graph of it. Okie dokie. 1200 divided by 1 plus 11 times e, which is in the functions on this one here. And okay, so in the graphing one, that's where it was different. There's, so down here in the functions, oh, whoops, I held it too hard. Over in the MISC, there's EXP, yeah, and that's pretty typical for if you're using any sort of kind of computer language. So EXP, and then in brackets, you have what your power is. So in this case, it's negative 0.2 times negative 0.2 times x. Your input is always your x. So even though we have t here, we're going to use x and bracket. Okay. So this thing, it looks like this, and we can kind of zoom out, and notice what happens. Try to click on this thing, is things start to plateau off, right? As x goes to infinity, things go to 1200. So we kind of get here, so at 10 years, that's the one we found. So at x equals 10, we have the intersection there at 482. Okay. That's what we found. So we can do another one. We wanted to find x equals 20. Okay, x equals 20. It's all a mess here. X equals 20 is here at 998.775. And then you can do the same thing for 30. 30 years. And we'd have to go up here. So at 30, the population size is at 1168-ish. Notice what happens is we run out of room in the pond, right? And so here there's not enough food, there's not enough, so things level off. And as the time goes on, the population kind of plateaus at 1200. Okay. So this is what we call a logistic growth. Okay, I see I'm out of time, But what I'll do is I'll take a screenshot of that graph that we just made and put it in here before I post the notes. And we'll keep going in with exponential and logarithmic equations next day. But make sure you have a breeze through. I think it's only a couple of pages, so have a look through those notes, try some of those problems. I'll see you on Thursday. And have a good Remembrance Day tomorrow. Any questions?